Hello, I'm Egecan Guler, a postdoctoral researcher at the University of Edinburgh. Our work in the Titan project focuses on making underwater optical wireless communication practical and affordable. In this video, I'm excited to show you how we've built a complete system that can stream real-time video from underwater using off-the-shelf components like a Raspberry Pi. The underwater world holds countless mysteries, but exploring it comes with a major challenge: the communication. Today's underwater vehicles and sensors generate huge amounts of data, but getting that data to the surface wirelessly is a big challenge. Traditional acoustic communication using sound waves works over long distances, but is painfully slow in the kilobits per second range, with noticeable delays too. Radio waves, which we rely on above the water, is absorbed by the seawater within centimeters. This forces expensive robots and sensors to surface just to transfer their data, wasting time, energy, and potentially missing crucial events. But there's a window of opportunity. Seawater allows blue-green light to pass through with relatively low absorption. This is the principle behind underwater optical wireless communication. By using light instead of sound, we can achieve data rates thousands of times faster than acoustics with virtually no delay. Laboratory demonstrations have shown incredible speeds, up to 25 gigabits per second and above. But here's the catch: these systems use expensive laboratory equipment. Our goal was different: build a practical, low-cost system that anyone could deploy. Our approach uses commercial off-the-shelf components centered around a Raspberry Pi microcontroller. The transmitter captures video with a standard camera module, compresses each frame, and sends it through a custom analog circuit that drives an LED. The light travels through the water, and on the other side, our receiver converts it back into video that can be streamed over the internet. The entire system costs a fraction of traditional underwater communication equipment, and it can run over 30 hours on a single battery pack. One of the biggest challenges underwater is keeping your transmitter and receiver aligned. Current, waves, and vehicle movement constantly shift positions. A traditional receiver with a narrow field of view would lose the signal instantly. Our solution is an angular diversity receiver, 13 photodiodes arranged in a dome pattern. This design captures light from a wide range of angles over 160 degrees, ensuring a stable connection even when there's movement due to waves. Here's our experimental setup. The transmitter sits at the bottom of a water tank inside a waterproof enclosure. A camera captures video of objects in the tank, demonstrating real-time underwater monitoring. The LED transmits data at 7 megabaud using simple on-off keying modulation. Above the water surface, our angular diversity receiver picks up the signal and sends it to a second Raspberry Pi, which streams the video to the cloud. The result: 18 frames per second video streaming with less than 100 milliseconds of delay. Fast enough for real-time monitoring and control applications. Our next steps include implementing bidirectional communication for command and control, allowing for more complex networks, and testing in real ocean environments. What we've demonstrated is that practical underwater optical communication doesn't require expensive laboratory equipment. With careful system design and affordable components, we can bring high bandwidth connectivity to the underwater world. This technology could enable networks of low-cost sensors for monitoring offshore wind farms, tracking marine wildlife, or supporting underwater robotics, applications that were previously too expensive to consider. We would like to acknowledge the funding support provided by the Titan project, and thank you for watching.
In this demonstration, we show how a SPAD array of arrays receiver can be used not only for communication, but also for sensing the transmitter's location or angle of arrival. The receiver consists of 16 SPAD subarrays, each providing an independent electrical output. When the optical transmitter illuminates the receiver, each subarray observes a different received signal strength, depending on its relative position within the imaging plane of the receiver. To illustrate this, we first measure the peak-to-peak voltage of the signal from one subarray. We then repeat the same measurement for a second subarray and compare the two outputs. Differences in the measured signal amplitude directly reflect the quantized spatial distribution of the incident optical power. By extending this measurement across all 16 subarrays, we can construct a two-dimensional heat map of received signal strength. From this heat map, and using geometric optics, the transmitter's direction or relative position can be inferred. This capability is particularly useful for applications such as user localization and tracking in an optical joint communication and sensing system, such as our air-to-water application.